So this will be my proof form to go along with 5.4, which is belts and bearings. I'm just going to talk about belts. Or I guess I'm just going to go through a belt problem here. You just be dealing with belt friction for that. So, yeah. And I forgot my BFS up there, sorry. But anyway, so yeah, we're talking about belt friction, and we're just gonna basically try to figure out what force, if you were pulling on this, I just have it attached to a wall, but the force acting on that wall to hold this object up. And here's our equation for that, T1 equals T2 times E to the mu. So it's E to our mu of friction times beta. Beta is an angle. It's actually the angle that this acts across. So if we look at this, I made it kind of convenient for myself, just a quarter of a circle, but so we know that this angle is then, it's a right angle, and this is the angle we want to find for beta. Now there's no trig function in front of beta, which means that you just kind of need to recognize that since there's no trig function, that beta must be in radians. So our value of beta will actually be pi over 2 because this is a 90-degree angle. And the way that you kind of think about this is it's the angle at which this belt is acting over its bearing or over its pulley, I guess you could say, or whatever like kind of smooth surface object is acting over, or whatever it's sliding over is what. So I mean that can be a cliff too if you really wanted it to be. If you were lowering an object or like over the side of a table, that would be kind of that's just the angle that's acting over. So yeah, and a couple things about our equation, because you can actually, so we can solve for the force to rate, like the force that would be almost raising this box, or the force to let this box down, and those are actually two different forces. So if you do it this way, where T1 is the force in the direction of motion, so the first one we're going to do is, I guess it's force in the direction of motion. T2 is a force against the motion. So the first one we're going to do is with the box going up, like this. So the weight that it takes, basically to keep the box from falling, like to support it and pull it, like the force we need to overcome will be greater than to raise this box. So we will be like this, and that means that in the direction, this is our T1 force. And this 200 pounds is our T2 force, because that's opposing our motion. We want to raise the box, but that force of that weight force is what's making the box go down. So now we're going to do a little solving here. So we have T1, which is this force, that's what we're looking for, times, or equals T2, so our force here, 200, times E, which is just our E, it's whatever, times 0.22. And then times this angle is acting over, which is 90 degrees, or in radians, pi over 2. And then we'll solve that quick. So, 200. And I get 282.56 pounds for that. Now, a way we can check this and see if it makes sense, if we just look at this, we don't really worry about any number other than this. This is pulling down with 200 pounds. If I want to raise that, I not only have to raise 200 pounds of it, I also have to go fight against the friction of this, because this is not rotating. Think of that as like the edge of a cliff or something. There's going to be friction against it, even if it's a smooth surface. So I have to do it. So if you're raising this box, it's the 200 pounds plus the friction here. So our answer should be greater than 200 pounds, and it is. So that's kind of a way to think of it, because if you're lowering that weight to 200 pounds, but that friction is also helping you, so you don't have to do quite as much work. And that's what we're gonna solve for next is, we're gonna flip these. Well, all we have to do is flip T1 and T2. So if you're T2 now, you're T1 now, this will give us the, it will give us the force that it takes to just about lower, like the point where the force, if it's a little less, the box will start lowering, kind of that threshold of motion. So here we're actually solving for T2, so T1 is 200. And everything will be the same, we're just solving for T2, so instead of multiplying all these, we'll actually divide T1 by our E, which you can see. Okay, so 200. That gives me a T2 value of 141.56. Now that makes me feel pretty good that we got the right answers there, because, like I said, so this one is kind of the diagram here, so I have to raise my 200-pound force, but then I also have to overcome the friction of the rock or the whatever I'm pulling against. So that should be greater, and this one should be less because it's the opposite. It's a 200-pound force, but there's friction helping me that's preventing it from pulling down as much. So that should be less. So that, yeah, so that should be how you, that would be how you would evaluate a problem like this with belt friction, where you have a belt system and you have some friction against the belt. Your biggest sticking point is probably just going to be finding this angle, and then remembering that beta must be in radians because there's no trig with it. So if you just have like an angle of 22, that's going to make it really weird, or an angle of 90, it's going to give you a really wrong answer. So make sure that this is in radians, and also that your calculator is in radians so that you get the correct answers for that. And the way to check that is, like I said, this should be greater if you're pulling up because it's 200 plus the friction, and then going down, it'll be 200 minus the friction. So yeah, that's belt friction to go along with 5.3, I think.